Look up at the night sky tonight, what do you see? A scattering of stars, a distant planet, perhaps the faint glow of the Milky Way. But what if I told you that every one of those pinpricks of light is a doorway to a story older than humanity itself? A story of cosmic cataclysms, ancient explosions, and mysteries so vast they bend the very fabric of time and space. This isn't just stargazing, it's time travel. Every beam of light reaching your eyes has journeyed across unimaginable distances, carrying whispers from the distant past. Some of those stars, they might not even exist anymore. Their light is a ghost, a final message from a world long gone. That's the magic of the cosmos. It doesn't just show us where we are, but when we are. Welcome to 26 Celestial Voyages Through Time, where we'll unravel the universe's greatest enigmas, one breathtaking discovery at a time. Think about this. The very atoms in your body were forged in the hearts of dying stars. You are quite literally made of stardust, a living remnant of cosmic events older than our solar system. That's the kind of awe we're diving into. From the mind-bending paradoxes of black holes to the explosive beauty of supernovae that lit up the sky before humans walked the Earth, we're embarking on a journey that stretches across billions of years. These aren't just scientific facts, they're chapters in an epic saga, and we've only just begun to read them. So why does this matter? Because the universe isn't some distant, untouchable realm, it's our shared inheritance. Every culture in history has looked up and wondered, weaving myths and legends to explain the heavens. Today we have telescopes instead of campfires, but the questions remain just as profound. What secrets do those swirling galaxies hold? How did the universe begin, and where is it taking us? The answers are out there, written in the language of light and time. And this video, it's your invitation to join the greatest adventure of all, the exploration of existence itself. So take a deep breath, because we're about to travel further than you've ever gone before. The cosmos is waiting. Let's begin. Our story begins not with a whimper, but with a roar, an eruption of energy so colossal it birthed reality itself. Picture this, an unfathomable moment nearly 14 billion years ago when all of space, all of time, all matter and energy we've ever known exploded into existence in a single searing instant. This wasn't just any explosion, it was the Big Bang, the ultimate Genesis event. But here, the mind-bending part. The universe didn't expand into space, space itself stretched, carrying matter along like raisins in rising dough. And we've got proof. That proof comes in the form of cosmic microwave background radiation, the faint afterglow of that primordial fireball. Imagine it as the universe's baby photo, a snapshot taken when everything was just 380,000 years old, a toddler by cosmic standards. This glow isn't random, it's speckled with tiny temperature variations, like cosmic fingerprints revealing where matter first clumped together, seeding the galaxies we see today. It's as if the universe left us breadcrumbs to trace its own origin story. Yet the deeper we dig, the stranger it gets. Some scientists propose a theory called inflation, a fleeting moment when the universe expanded faster than light itself, smoothing out wrinkles in space-time like an iron over cosmic fabric. And then there's the multiverse hypothesis, suggesting our Big Bang might have been just one bubble in a frothing sea of universes, each with its own laws of physics. Think about that, alternate realities where gravity repels, where time runs backward, where stars never formed. But the grandest mystery remains. How did something emerge from nothing? Quantum fluctuations, vacuum energy, equations scribbled on blackboards, we're piecing together a puzzle with half the pieces missing. What we do know is this: every atom in your body, every planet, every star owes its existence to that first unimaginable moment. The Big Bang wasn't just the start of the universe, it was the start of time itself. And that's where our voyage truly begins. Now let's turn our gaze to one of the most baffling riddles in modern astronomy. A mystery so pervasive it makes up 85% of all matter in the universe, yet remains utterly invisible to our eyes and instruments. We're talking about dark matter, the cosmic ghost holding galaxies together while slipping through our fingers like smoke. Picture a spiderweb you can't see, its delicate threads stretching across the cosmos, sculpting the universe's grand structure with an unseen hand. How do we know it's there? The clues are everywhere. Stars on the outer edges of spiral galaxies orbit so fast they should fling into the void, yet something's gripping them with gravitational glue. Light bends around empty patches of space as if tugged by hidden mass. Even the way galaxy clusters move suggests an invisible scaffolding, a skeleton we can't see but can't ignore. It's like watching marionettes dance and realizing there must be strings, even if you can't spot them. Scientists have turned the planet into a dark matter detective agency. Deep underground, in abandoned gold mines and beneath mountains, ultrasensitive detectors wait for the faintest whisper of a collision, a dark matter particle bumping into ordinary matter. Meanwhile, the Large Hadron Collider smashes protons together at nearly light speed, hoping to create these elusive particles in miniature Big Bangs. An orbiting telescope scans the skies for distorted starlight, mapping dark matter's shadowy fingerprints. The theories get wilder the deeper you dig. Some suggest dark matter could be primordial black holes left over from the universe's first seconds. Others propose it's evidence of extra dimensions, particles from a parallel reality leaking into ours. There's even a radical idea that dark matter isn't matter at all, but a flaw in our understanding of gravity itself. Imagine rewriting Newton, and because the universe played a trick on us. Here, what makes this hunt so thrilling? Dark matter isn't just missing matter, it's missing history. If we find it, we might uncover secrets about how galaxies formed, why the universe looks the way it does, even what happened in those first chaotic moments after creation. It's humbling to realize we've been studying the cosmos like someone reading a book by moonlight, only now realizing most pages were written in invisible ink. Every failed detection, every puzzling result isn't a dead end. It's the universe nudging us to think bigger. After all, the greatest discoveries begin when we admit how much we don't know. If dark matter is the universe's invisible scaffolding, then dark energy is its silent rebel, a force so strange it makes galaxies flee from each other faster than gravity can pull them together. Picture the cosmos as a loaf of raisin bread baking in an oven. As the dough expands, every raisin moves away from the others. But what if the oven suddenly turned up the heat, making the dough swell faster and faster? That's dark energy in action, an enigmatic pressure stretching space itself, pushing the universe toward an unknown destiny. The story of this discovery reads like a cosmic detective thriller. In the late 1990s, two teams of astronomers were studying distant supernovae, exploding stars so bright they outshine entire galaxies. These stellar fireworks should have been reliable cosmic yardsticks, revealing how fast the universe expanded in the past. But the data told a shocking tale. Instead of slowing down as gravity tugged everything inward, the expansion was speeding up. It was as if you tossed a ball in the air, only to watch it rocket skyward, defying all logic. This revelation was so groundbreaking it earned the researchers the Nobel Prize in 2011, rewriting cosmology in a single stroke. So what exactly is dark energy? The leading theory points to an old cosmological constant, a kind of energy woven into the fabric of space itself. Empty space, it turns out, might not be empty at all. Quantum physics suggests it's a bubbling sea of virtual particles flickering in and out of existence, generating a repulsive force. But here's the catch. Calculations predict this energy should be a staggering 120 orders of magnitude stronger than what we observe. That's like expecting a hurricane and feeling only a breeze, a discrepancy so huge it hints we're missing something fundamental. Alternative theories abound. Maybe dark energy isn't constant but evolves over time, a field called quintessence that changes its strength. Or perhaps theory of gravity breaks down on cosmic scales, requiring entirely new physics. Some even speculate dark energy could be the signature of another universe brushing against ours in higher dimensions. The wildest idea. That we're seeing the first clues of the universe's eventual death, a big rip where dark energy grows so powerful it shreds galaxies, stars, even atoms themselves, leaving space cold and empty. Yet amid these dizzying possibilities, one truth stands clear. Dark energy holds the universe's fate in its grip. Will expansion continue gently, leaving galaxies isolated like distant campfires in an endless night? Or will the acceleration become so extreme it tears reality apart? For now, telescopes like the Dark Energy Survey and the upcoming Nancy Grace Roman Space Telescope are mapping billions of galaxies, searching for answers in the subtle war between gravity and this phantom force. Every observation, every calculation brings us closer to solving one of existence's greatest puzzles, a reminder that the cosmos is far stranger and far more wondrous than we ever imagined. Imagine a place where gravity wins the ultimate battle, where space and time twist into knots so tight that not even light can fight free. Black holes aren't just cosmic vacuum cleaners. They're the universe's most extreme laboratories, bending the rules of physics until they shatter. And for decades, we thought nothing escaped their grip, until Stephen Hawking turned that idea on its head. Hawking's groundbreaking insight: black holes can leak. Near the event horizon, that point of no return, quantum fluctuations create particles that siphon energy from the black hole itself, slowly evaporating it over eons. This Hawking radiation was a bombshell. It meant even these monstrous voids have an expiration date. But here, where things get messy. According to quantum mechanics information, the blueprint of everything that falls into a black hole can't be destroyed. Yet if the black hole vanishes, what happens to that data? This is the black hole information paradox, a clash between relativity and quantum theory that's kept physicists awake for 50 years. Then came the Event Horizon Telescope's triumph in 2019, the first ever image of a black hole's shadow, a fiery ring framing the abyss at the heart of galaxy M87. That glowing wasn't just a pretty picture. It was a test of theories under the most extreme conditions. The result: general relativity passed with flying colors, but the mystery only deepened. How can a black hole obey rules while simultaneously defying quantum law? Some theorists argue information escapes encoded in Hawking radiation, like smoke signals from a burning library. Others propose wilder solutions: holographic universes where data gets smeared across the event horizon, or wormholes linking black holes to alternate realities. The boldest idea: that black holes might birth new universes with their own laws of physics forged in the collapse. What's clear is this: every breakthrough peels back another layer of the paradox, revealing how little we truly grasp about the fabric of reality. Black holes aren't just cosmic oddities, they're keys to unlocking the universe's deepest secrets. And as we stare into that darkness, we're not just observing the abyss, we're asking it to rewrite the rules of existence itself. Picture a cosmic subway system, tunnels carved through the very fabric of space-time, connecting distant corners of the universe in the blink of an eye. These are wormholes, not just the stuff of sci-fi dreams, but real mathematical predictions of general relativity. The equation suggests space-time could fold like a piece of paper, bringing two distant points together. Punch a hole through that fold and you've got a shortcut across the cosmos. But here's the catch: these theoretical tunnels are notoriously unstable. Without some cosmic duct tape, they'd collapse faster than you could say black hole. That's where exotic matter comes in, a hypothetical substance with negative energy that could prop open a wormhole's throat like scaffolding in a mine's shaft. Think of it as anti-gravity glue, counteracting the natural tendency of space-time to snap back into place. The problem: we've never observed exotic matter in the wild. It exists in math equations and quantum labs as fleeting virtual particles, but harvesting enough to stabilize a wormhole would be like trying to build a skyscraper out of soap bubbles. Pop culture adores wormholes for their storytelling potential. From the watery vortex in Interstellar, painstakingly modeled by physicist Kip, to Star Trek's convenient jumps across the galaxy, these portals offer narrative gold, but reality is far messier. Even if a wormhole existed, traversing it might require speeds faster than light or expose travelers to lethal tidal forces. One miscalculation and you're not just lost in space, you're spaghettified. Yet the most tantalizing possibility isn't just crossing space, it's crossing time. Some models suggest a wormhole could link not just locations but eras, with one end aging slower due to relativistic effects. Imagine stepping through and meeting your own ancestor. But before you draft that letter to your past self, consider the paradoxes. If you prevent your own birth, who steps through the wormhole? The universe abhors such contradictions, which is why many physicists suspect nature slams these doors shut with quantum laws we don't yet understand. So are wormholes cosmic fact or mathematical fiction? For now, they live in the twilight between theory and observation, a reminder that the universe often outpaces our imagination. Whether they're bridges to other worlds or elegant mirages, one thing's certain: their mystery keeps us reaching for the stars. Time isn't the steady, unchanging river we imagine. It's more like a stretchy cosmic fabric, warped and woven by gravity and motion in ways that defy common sense. His theory of relativity revealed this stunning truth. The faster you move or the closer you are to a massive object, the slower time ticks for you compared to someone else. This isn't science fiction, it's measurable reality. Atomic clocks flown on airplanes tick ever so slightly slower than their earthbound twins, and even the GPS satellites guiding your phone have to account for time dilation, or their navigation would drift off by miles. Now picture this: identical twins born under the same stars. One becomes an astronaut, embarking on a near-light-speed journey to a distant star, while the other stays home. When the traveling twin returns, they might step off the ship to find their sibling has aged decades more than they have. This twin paradox isn't a thought experiment. It's a consequence of relativity so well established that engineers have to correct for it in real-world technology. The universe doesn't just allow time travel into the future, it demands it under the right conditions. But here, where it gets even wilder. Imagine an astronaut venturing close to a black hole, where gravity's grip distorts time like a funhouse mirror. To them, minutes might pass, but back on Earth, centuries could slip by. They'd return to a world where everyone they knew is gone, where cities have risen and fallen, where humanity might have spread to the stars, all while they experience just a brief voyage. This isn't fantasy, it's the universe's own rulebook. Yet time dilation isn't just a cosmic quirk, it's a doorway to profound questions. If time is fluid, what does that mean for the idea of now? Is the present moment universal, or does it shift depending on where you are and how you're moving? The answers ripple through philosophy and physics alike, challenging our most basic assumptions about reality. For future astronauts, time dilation could be both a blessing and a curse. A trip to Alpha at near light speed might feel like a few years to the crew, but Earth would have moved on without them. Colonies on distant worlds could evolve separately, their calendars drifting out of sync with Earth's. The very concept of a shared human timeline might unravel as we spread across the galaxy. This revelation that time is a dimension as malleable as clay changes everything. It means the universe is far stranger than we ever dreamed, that the ticking of a clock isn't absolute but a whisper in the grand symphony of space-time. And if we ever master the art of bending time, even a little, we won't just be exploring space, we'll be navigating the fourth dimension itself. The universe is vast beyond comprehension. Trillions of galaxies, each brimming with billions of stars, many hosting planets in the perfect Goldilocks zone for life. With numbers this staggering, the math seems undeniable. Intelligent civilizations should be everywhere. So why does the cosmos feel so silent? This is the Fermi Paradox, a question that haunts astronomers like a cosmic ghost story. If life is probable, where is everybody? One chilling answer is the Great Filter, a hypothetical barrier that prevents life from advancing too far. Maybe the filter is behind us, some improbable fluke that made Earth uniquely suited for complex life. Or worse, maybe it's ahead of us, lurking in our future like a tripwire. Nuclear war, climate collapse, runaway AI, could every advanced civilization inevitably engineer its own demise? The unsettling truth is that every ancient ruins on Earth whispers the same lesson: even mighty societies fall. If this filter exists, crossing it might be the greatest challenge humanity ever faces. But not all theories are so bleak. The zoo hypothesis suggests we're being deliberately ignored, like animals in a cosmic wildlife preserve. Advanced civilizations might be watching from a distance, waiting for us to reach some maturity before making contact. It's a comforting thought until you consider who gets to decide when we're ready. Another idea: we're simply too primitive to recognize the signals. Alien communication might be as invisible to us as Wi-Fi would have been to medieval farmers. Then there's the WOW signal, a 72-second burst of radio waves detected in 1977, so perfectly aligned with extraterrestrial predictions that the astronomer who found it scribbled "wow" in the margins. Decades later, we still don't know what caused it. Was it a cosmic hiccup or a hello we failed to answer? Projects like SETI keep listening, scanning the skies for patterns amid the noise, but space is big and needles are small. Perhaps the answer is simpler: we're early. The universe is 13.8 billion years old, but it might still be in its infancy for intelligent life. Stars will burn for trillions more years. What if we're among the first to ask these questions? Or maybe life is rarer than we think and Earth is a lonely miracle. Either way, the silence isn't just a mystery, it's a mirror. How we interpret it says as much about us as it does about the cosmos. Are we survivors who beat the odds, or cautionary tales waiting to happen? The stars aren't talking. Yet, on a quiet August night in 1977, a radio telescope in Ohio picked up a signal so extraordinary that it still echoes through the halls of astronomy. For 72 seconds, a burst of radio waves blazed across the dial at the exact frequency scientists predicted extraterrestrials might use. A cosmic shout in the key of hydrogen, the universe's most common element. The astronomer who spotted it circled the data in red pen and scribbled "wow" next to it, giving the signal its now iconic name. Then, just as suddenly as it appeared, the transmission vanished, never to repeat. Decades later, we're still chasing its ghost. Was it a message from another civilization or something more mundane? Skeptics point to natural explanations, like a passing comet reflecting sunlight in just the right way. But here's the catch: comets don't emit narrowband radio waves at that frequency, and none were recorded in that patch of sky at the time. Others suggest it might have been a military satellite or a rogue signal bouncing off space debris. Yet nothing in human technology matches its unique fingerprint. The WOW signal remains stubbornly unexplained, a cosmic riddle wrapped in static. What makes this so tantalizing is the math. The signal originated near the constellation Sagittarius, where billions of stars and potentially habitable planets crowd the Milky Way's core. If it was artificial, the transmitter would need power dwarfing all of Earth's energy output combined. Imagine a civilization capable of such engineering. Why would they send a fleeting hello? Unless, of course, it wasn't meant for us. Like overhearing a fragment of a conversation meant for someone else, we might caught a cosmic whisper never intended for human ears. Modern projects like Breakthrough Listen now scan the skies with AI, sifting through radio noise for patterns that human eyes might miss. New telescopes like the upcoming Square Kilometre Array will eavesdrop on the universe with unprecedented sensitivity. But the WOW signal's legacy isn't just about finding aliens. It's a humbling reminder of how little we've heard. The universe has been broadcasting for billions of years. We've barely tuned in for a century. Every unexplained blip on the radar isn't just noise. It's a potential thread in a conversation we're only beginning to understand. Perhaps the most profound lesson of the WOW signal is this: absence of proof isn't proof of absence. Space is vast, time is long, and the odds are good that someone somewhere is listening too. Whether the signal was a cosmic coincidence or a deliberate call, it ignited something timeless in us, the hope that we're not alone in the dark. And until we know for sure, the universe keeps sending its mysteries, one fleeting whisper at a time. In October 2017, astronomers spotted something that shattered our understanding of cosmic visitors: a mysterious object tumbling through our solar system at breakneck speed. This wasn't just another asteroid or comet. It came from beyond, the first confirmed interstellar traveler ever detected. They named it Hawaiian for scout or messenger from afar, and its brief appearance sparked a firestorm of debate that still burns today. What made so extraordinary? First, its shape. A bizarre, elongated cigar roughly 10 times longer than it was wide, unlike any natural object we've seen in our solar system. Then there was its motion. As it hurtled past the sun, it didn't just glide on gravity's rails, it accelerated as if pushed by some unseen force. Comets speed up when their icy surfaces vaporize, creating a visible tail, but left no trail of gas or dust. It moved like a sail catching sunlight. Only nothing in nature behaves that way. The scientific community split into camps. Mainstream astronomers argued it was a peculiar type of asteroid or a rare, dark comet with invisible outgassing. But astrophysicist Avi proposed a more radical idea: could be artificial, a light-powered probe or a fragment of alien technology. The speculation wasn't baseless. Its brightness fluctuated wildly, suggesting a tumbling, metallic surface, and its trajectory seemed oddly optimized for a slingshot around the sun. Yet the truth remains elusive. By the time we spotted, it was already racing away, too distant for detailed observations. Was it a shard of a shattered planet, a cosmic iceberg, or something even stranger? The data left gaps wide enough to fuel dreams of extraterrestrial contact and rigorous skepticism. One thing certain was a wake-up call. The universe isn't static. It's a dynamic highway where interstellar objects might zip through our neighborhood more often than we realized. New telescopes like the observatory will soon scan the skies for more of these visitors, ready to decode their secrets. Until then, lingers as a tantalizing enigma, a silent wanderer that came, confounded, and vanished into the dark, leaving us to wonder what else might be out there, drifting between the stars. Right now, as you sit there watching this video, you, along with every star in the Milky Way, are hurtling through space at over 1,000,000 miles per hour towards something we can't even see. This isn't science fiction, it's the reality of the Great Attractor, a gravitational monster so powerful it's bending the paths of entire galaxies like a cosmic magnet. But here's the twist: we're flying blind toward it. Our view of this enigmatic force is blocked by the thick dust and stars of our own galaxy's bulge, a region astronomers call the zone of avoidance. It's like trying to spot a lighthouse through a sandstorm. Only this lighthouse might hold clues to the fate of our galactic neighborhood. For decades, the Great Attractor was little more than a shadow on the cosmic map. Scientists first noticed its pull in the 1970s when they mapped the motion of galaxies and realized something was off. Instead of drifting apart evenly with the universe's expansion, thousands of galaxies, including ours, were being dragged off course, as if caught in a river's current. The math pointed to a concentration of mass equivalent to tens of thousands of Milky Ways, all clustered in a spot obscured by our own galaxy's dust. How do you study something you can't see? The answer lies in light our eyes can't perceive. Infrared telescopes like NASA's Spitzer and the European Space Agency's became our cosmic X-ray glasses, peering through the zone of avoidance by detecting heat signatures rather than visible light. What they revealed was staggering. The Great Attractor isn't just a lone anomaly. It's part of an even larger web of gravity, anchored by the mind-bending supercluster, a filament of galaxies spanning 500 million light-years, with the Great Attractor as its beating heart. Imagine a spider web where every thread is a galaxy, and the spider sits at the center, tugging ever so slightly on each strand. But the deeper mystery isn't just what the Great Attractor is, it's why it exists at all. Some theories suggest it's the core of an ancient collision, where multiple galaxy clusters merged into a gravitational titan. Others propose it's a signpost pointing to something even grander, the supercluster, a behemoth of matter lurking beyond it, pulling the Great Attractor itself. And then there's the wild card. Could it be evidence of exotic physics, a wrinkle in space-time we haven't yet imagined? What's certain is this: the Great Attractor humbles us. Even as we map the cosmos with ever-sharper precision, our trajectory is still governed by forces we've only begun to understand. Every galaxy in our supercluster is riding this gravitational wave toward an unseen destiny, a reminder that the universe is less like a static painting and more like a river, carrying us all toward mysteries waiting just beyond the veil. Imagine a world where the ground beneath your feet isn't rock or sand, but a vast, glittering plain of diamond, a planet so rich in carbon that its very core has crystallized into a cosmic jewel. Welcome to 55E, a scorching inferno of a world orbiting its star so closely that a single year lasts just 18 hours. At first glance, this sounds like something ripped from a pirate's treasure map, but the science behind this diamond planet is even more fascinating than fiction. Discovered in 2004, 55E quickly stood out as one of the most bizarre exoplanets ever found. Roughly twice Earth's size, but nearly 9 times as massive, its density hinted at a composition unlike anything in our solar system. Here's the kicker: its parent star is unusually carbon-rich, meaning the planet likely formed from material brimming with this element. Under the crushing pressure of its own gravity and the star's blistering heat, carbon could have been compressed into diamond, a literal gemstone world. Picture continents of graphite and oceans of molten diamond, with skies so hot they'd vaporize metal. But before you dream of interstellar mining expeditions, consider the challenges. The planet's surface temperature exceeds 2,000 degrees Celsius, hot enough to melt steel. Its day side is a permanent lava ocean, while its tidally locked night side might harbor slightly cooler, but still deadly conditions. Even if we could reach it, harvesting diamonds from this hellscape would be like trying to sip water from a volcano. The real magic of 55E isn't just its sparkle, it's what it teaches us about planetary diversity. Our solar system, with its rocky and gaseous worlds, might be the exception rather than the rule. Out there, in the infinite variety of the cosmos, planets could be made of diamond, iron, or even stranger materials we've yet to imagine. This glittering enigma reminds us that the universe's creativity knows no bounds, and that sometimes the most fantastical stories are written not in myth, but in the cold, hard light of distant stars. Some stars flicker like candles in the wind, but none have baffled scientists quite like KIC 8462852, better known as Tabby's star. Named after astronomer who first documented its bizarre behavior, this unassuming star in the constellation Cygnus doesn't just dim, it plunges in brightness by up to 22%, in irregular, dramatic dips that last days or weeks. Imagine that unpredictably flickers between blinding and nearly off, with no discernible pattern. That's the cosmic riddle we're facing. When the Space Telescope first spotted these anomalies in 2015, the data all conventional explanations. Planets passing in front of stars create predictable repeating shadows, but Tabby's star dimmed erratically, as if something enormous and misshapen were drifting across its face. The strangest dip, a staggering 22% drop in brightness, suggesting an object nearly half the star's width blocking its light. For comparison, Jupiter passing in front of our Sun would cause just a 1% dimming. Whatever was eclipsing Tabby's star was something on a scale we'd never seen. Cue the alien megastructure hypothesis. Astronomer Jason Wright proposed a radical idea. Could these dips be caused by a swarm, a colossal array of energy-harvesting panels built by an advanced civilization? The concept, first imagined by physicist Freeman, involves surrounding a star with solar collectors to capture its power. If such a structure existed, it might explain the star's erratic dimming as massive panels or orbital debris passed by. The internet erupted with speculation, and for a moment, science fiction seemed to brush shoulders with reality. But before we draft welcome speeches for our cosmic neighbors, let's examine the natural suspects. One leading theory points to swarms of dust clouds, possibly from shattered comets or colliding planets, creating a chaotic debris field. Observations revealed the star's light was being blocked more at shorter wavelengths, exactly what you'd expect from fine dust particles. Another idea involves a giant, misshapen planet with colossal rings or a trailing swarm of asteroids, casting uneven shadows as it orbits. There's even a hypothesis that the star itself might be recovering from a catastrophic collision, cloaked in lingering fragments of its own destruction. Here, where Tabby's star becomes more than a curiosity, it's a litmus test for how we approach cosmic mysteries. The scientific method demands we exhaust every natural explanation before invoking aliens, but the allure of the unknown is irresistible. This star forces us to confront our biases. Are we too quick to dismiss extraordinary possibilities, or too eager to see aliens in every shadow? The latest data leans toward the mundane. Dust seems the likely culprit, but the case isn't closed. Tabby's star remains an curiosity, reminding us that the universe loves to defy expectations. Whether it's alien megastructures or cosmic dust bunnies, one truth shines through. The cosmos is always more creative than we are. And sometimes the real treasure isn't the answer, it's the question itself. Stretching 7 light-years high, the pillars of creation stand as one of the most breathtaking sights in the cosmos. 3 colossal towers of interstellar gas and dust where stars are born. When the Space Telescope first captured this iconic image in 1995, it revealed the Eagle Nebula's secret. These billowing structures aren't just beautiful, they're active stellar nurseries, forging new suns from the raw material of the universe. But here's the twist that haunts astronomers. We might be looking at a cosmic ghost. These pillars could already be gone, blasted apart by a supernova shockwave thousands of years ago. The light carrying that destruction simply hasn't reached us yet. Inside these swirling columns, gravity works its magic. Dense knots of gas collapse under their own weight, heating up until nuclear fusion ignites. A star is born. The pillars' darker patches aren't empty, they're globules, thick cocoons of dust shielding infant stars from the violent radiation of nearby stellar siblings. Like cosmic incubators, they nurture these protostars until they're strong enough to blow away their dusty blankets and shine on their own. Infrared vision later pierced through the obscuring dust, revealing fledgling stars tucked inside, their fiery births hidden from visible light. Yet the very forces that create stars also destroy them. The Eagle Nebula is home to massive, short-lived stars destined to explode as supernovae. In 2007, the Spitzer Space Telescope detected a shockwave that might already obliterated the pillars. We just can't see it because light takes 7,000 years to travel from the nebula to Earth. It's a staggering thought. We're simultaneously witnessing the pillars' glory and their potential demise, separated only by time's cruel delay. This paradox makes the pillars of creation more than a pretty picture. They're a lesson in cosmic impermanence. The universe sculpts its masterpieces only to erase them, like a sand artist whose work is washed away by the tide. New observations suggest the pillars are being eroded by stellar winds, their intricate shapes slowly dissolving into the void. Even if a supernova hasn't claimed them yet, their fate is sealed. But destruction here breeds creation elsewhere. The same shockwaves that tear down these towers will compress nearby gas, triggering the birth of future stars. The cycle continues, as it has for billions of years. What makes this celestial landmark so poignant is its duality. It's both a cradle and a graveyard, a monument to the universe's relentless cycle of death and rebirth. Those towering pillars remind us that beauty in the cosmos is fleeting, that every star we see is just a momentary spark in the grand timeline of existence. And perhaps that's the most profound message of all. The universe doesn't create forever. It creates for now, teaching us to marvel at its wonders while they last. Among the countless clusters and superclusters that weave the universe's grand tapestry, there exists a place so unsettlingly empty it defies logic, the void. Stretching an astonishing 330 million light-years across, this cosmic desert holds barely 60 galaxies where there should be thousands. Picture a sphere of darkness so vast it could swallow our entire local group of galaxies with room to spare, leaving nothing but an eerie silence. Astronomers call it the Great Void, and its existence shakes our understanding of how the universe structures itself. How can a region this large be so empty? The answer might rewrite cosmology itself. The discovery of the void in 1981 sent shockwaves through astronomy. Surveys mapping galaxy distributions expected matter to be spread relatively evenly, like foam in an ocean. Instead, they found this gaping hole, a place where the universe forgot to build. To grasp its scale, imagine flying through it at light speed. You travel for hundreds of millions of years without encountering more than a handful of galaxies. Most voids are small, mere bubbles between galactic filaments, but the void is a vacuum on a scale that shouldn't exist. It's as if someone took an eraser to the cosmos. Theories attempting to explain this anomaly range from the plausible to the fantastical. One leading idea suggests it's a relic of the early universe, where quantum fluctuations left a region devoid of density variations, a cosmic oversight where matter never clumped together. Others propose it's the aftermath of a collision between our universe and another bubble in the multiverse, a scar from a primordial crash that swept matter aside like a celestial plow. But the most provocative hypothesis, that an advanced civilization, far beyond our comprehension, might have harnessed the energy of entire galaxies, leaving behind a sterile void. While there's no evidence for this, it forces us to reckon with how little we know about the universe's potential for intelligence. What makes the void truly humbling is its challenge to the Copernican principle, the idea that we don't occupy a special place in the cosmos. If voids this vast exist, could our corner of the universe be an outlier, or worse? What if the universe is far emptier than we thought, and we're simply living in an unusually crowded neighborhood? Every galaxy every star we've named, might be part of a rare oasis in an endless desert. Yet even emptiness holds clues. The void's few galaxies are oddly isolated, evolving in solitude without the gravitational dance that shapes most galactic lives. Studying them could reveal how galaxies behave when left alone for billions of years, like experiments in cosmic isolation. And as telescopes grow more powerful, we might find smaller voids scattered like hidden rooms in the universe's mansion, each one a puzzle waiting to be solved. The void isn't just a curiosity, it's a mirror reflecting our ignorance. For all our maps and models, the cosmos still reserves the right to surprise us. Whether it's a statistical fluke, a wound, or something beyond our current physics, this vast nothingness whispers a truth we're only beginning to accept. The universe is stranger and far more mysterious than we ever dared to dream. Beyond the orbit of Neptune, where sunlight is little more than a faint star in the eternal twilight, lies a frozen graveyard of cosmic leftovers, the Belt. This vast-shaped region is home to Pluto, once considered our solar system's 9th planet, now the king of a growing dynasty of dwarf planets. But Pluto is just the beginning. Lurking in this icy darkness are worlds like Eris, a dwarf planet so massive it triggered Pluto's reclassification, and a spinning egg-shaped oddity that completes a full rotation every 4 hours, flinging icy debris into space like a celestial sprinkler. These aren't just frozen rocks, they're time capsules, preserving secrets from the solar system's violent infancy. The belt is more than a collection of icy relics. It's a cosmic crime scene, and the clues point to a missing suspect. Astronomers have noticed something peculiar. The orbits of distant belt objects tilt and cluster in ways that defy gravity's usual rules. The math suggests an unseen hand, a hidden planet, perhaps 5 to 10 times Earth's mass, lurking so far out that a single orbit could take 20,000 years. They call it Planet 9, and if it exists, it would rewrite our solar system's family tree. Imagine a world so distant that even our most powerful telescopes struggle to spot it, its presence betrayed only by the gravitational whispers of smaller objects dancing to its tune. Why does this matter? Because the belt is the solar system's attic, a place where forgotten remnants of planetary formation have gathered dust for billions of years. Every odd orbit, every unusual composition is a puzzle piece in understanding how giant planets like Jupiter and Saturn migrated, how Earth got its water, and whether our cosmic neighborhood is unique. Take the most distant object ever visited by a spacecraft. When New Horizons flew past it in 2019, it revealed a pristine binary world, 2 lobes gently fused together like a cosmic snowman, untouched since the dawn of the solar system. This wasn't just a flyby, it was a look back in time. Yet for all we've learned, the belt remains a frontier. New telescopes like the observatory are about to flood us with discoveries, potentially spotting Planet 9 or revealing even stranger worlds. Some scientists speculate there could be objects the size of Mars hiding in the darkness, or rogue exoplanets captured from other stars. Others wonder if the belt holds the key to Earth's oceans. Did comets from this frozen zone deliver the water that fills our seas? The belt reminds us that our solar system is far from fully explored. Every new discovery peels back another layer of the mystery, showing us that even in our own cosmic backyard, the universe still has surprises up its sleeve. Whether it's the hunt for Planet 9 or the next bizarre dwarf planet, one thing's certain: the outer solar system isn't empty. It's just waiting for us to look closer. Right now, as you read these words, an unstoppable cosmic dance is unfolding, one that will reshape the night sky for civilizations billions of years from now. The Andromeda galaxy, that faint smudge of light visible on clear nights, isn't just our celestial neighbor, it's our future collision partner, hurtling toward the Milky Way at 250,000 miles per hour. In about 4 billion years, these 2 titans will meet in a gravitational embrace, a merger so slow and delicate that stars will pass through one another like phantoms in the night. Forget Hollywood's fiery explosions. This is a collision where emptiness is the rule, not the exception. Picture the scale of this event. Both galaxies contain hundreds of billions of stars, yet the average distance between them is so vast that direct stellar collisions will be vanishingly rare. Instead, gravity will twist and stretch both galaxies like taffy, their spiral arms unraveling into great tidal streams of stars. Over millions of years, their cores will swing past each other in a cosmic do-si-do, eventually settling into a single, football-shaped elliptical galaxy astronomers nicknamed the night sky from a hypothetical future Earth, a breathtaking canvas of unfamiliar constellations, with Andromeda's stars no longer a distant blur, but scattered across the heavens like diamond dust. Here's the twist: while the merger will be spectacular, it'll be surprisingly safe. The solar system might get flung to the galaxy's outskirts or dance closer to the core, but the odds of our sun or planets being destroyed are astronomically low. The real danger comes from the gas and dust between stars. As these clouds collide, they'll trigger a fireworks show of star formation, with newborn suns igniting across the sky. Some of these stellar nurseries might birth massive stars destined to explode as supernovae, bathing nearby planets in radiation. Yet even this drama unfolds over timescales so long that entire species could rise and fall between celestial fireworks. What's truly humbling is imagining how future civilizations, if any still exist, might witness this event. With telescopes far beyond our own, they could map the gravitational tides reshaping their galaxy in real time, watching as familiar star patterns stretch into unrecognizable shapes. Would they feel awe or dread? Would they see it as an ending or a rebirth? The merger's slow-motion grandeur offers a profound perspective. Galaxies aren't static islands but dynamic creatures, constantly evolving through collisions that are less like car crashes and more like rivers merging into a greater sea. Yet this cosmic ballet also hints at a deeper truth. The universe's largest structures are bound by gravity's patient hand, their fates written in motions too slow for human eyes to perceive. In the grand timeline of the cosmos, even galaxies are fleeting, their collisions just brief chapters in a story where only space and time endure. So the next time you spot Andromeda in the night sky, remember, you're not just looking at another galaxy. You're glimpsing the future, a silent promise written in starlight that outlives us all. Imagine the universe as a living organism, not with flesh and blood, but with threads of dark matter and glowing gas stretching billions of light years, connecting galaxies like neurons in a cosmic brain. This is the cosmic web, the hidden architecture of existence itself. If you could see it with naked eyes, the night sky wouldn't just be scattered stars. It would be a labyrinth of luminous filaments, a spider's silk spun on the grandest scale imaginable. And just like the veins in a leaf or the roots of a tree, this web holds the secret to how the universe grew from a featureless sea of particles into the structured cosmos we know today. The story begins with the faintest ripples in the early universe, tiny fluctuations in density left over from the Big Bang. Over billions of years, gravity amplified those ripples, pulling dark matter into vast, winding rivers. Ordinary matter, the stuff of stars and planets, followed these invisible highways, pooling where filaments crossed like cosmic intersections. These knots grew into galaxies, while the threads between them remained mostly empty, save for wisps of hydrogen gas so thin a single cubic meter might hold just one atom. Yet despite their near invisibility, these filaments are the universe's backbone, channeling material across unimaginable distances. Scientists map this web indirectly, using quasars, distant galaxies with supermassive black holes so bright they act like cosmic flashlights. As their light travels through filaments, certain wavelengths get absorbed, leaving fingerprints in the data. It's like shining a light through a stained glass window and studying the colors that come through to reconstruct the glass's pattern. Other methods involve tracking the motion of galaxies, which subtly tug on one another through the web's gravitational pull. The result, a growing atlas of the universe's hidden highways, revealing a structure so vast it makes our Milky Way feel like a speck of dust on a grand cathedral's ceiling. What's truly mind-bending is how this web mirrors other complex systems in nature. The branching patterns of neurons in a human brain, the mycelium networks of fungi beneath a forest floor, even the distribution of cities and roads on Earth, all echo the cosmic web's design. Scientists call this scale invariance, the idea that certain shapes repeat across wildly different sizes and contexts. It's as if the universe has a favorite blueprint, one it uses whether building a galaxy cluster or a single cell. Yet the cosmic web isn't static. It's a dynamic, ever-changing scaffold. Shockwaves from colliding galaxy clusters send ripples through the filaments, while supermassive black holes pump energy into the voids, creating vast bubbles of heated gas. Some theorists even suggest that dark energy, the mysterious force accelerating the universe's expansion, might be stretching the web itself, thinning its threads over trillions of years until galaxies drift apart like unmoored ships. For astronomers, studying this web isn't just about mapping the present, it's about decoding the past. By simulating its growth in supercomputers, they can rewind time to test theories about dark matter's nature or the universe's initial conditions. Each new observation sharpens the picture, like adjusting a telescope's focus until the blur becomes sharp. And as we peer deeper, we're left with a humbling thought. The universe isn't a random scattering of stars. It's a meticulously woven tapestry, its patterns written in the language of gravity and time, a masterpiece we're only beginning to read. We think we know the moon, our silent companion, a gray rock hanging in the sky, seemingly unchanging. But buried in its ancient lava plains lies a secret that upends everything. The moon once had a magnetic field stronger than Earth's, a protective shield that vanished without a trace. This isn't science fiction. Apollo astronauts brought back rocks that tell this forgotten story. Their microscopic crystals locked in time like tiny compass needles pointing to a moon that crackled with magnetic energy billions of years ago. How could a world 1/4 Earth's size, long considered geologically dead, muster such power? And why did it disappear? The answers might rewrite not just lunar history, but our understanding of how planets live and die. Those Apollo samples hold the key. When molten rock cools, minerals like magnetite align with the planet's magnetic field like iron filings around a bar magnet, freezing that direction in stone. Studies of lunar basalts revealed something astonishing. Some crystals pointed to fields 50 times stronger than today's moon could possibly produce. That's like finding a fossilized lightning bolt in a desert. The implication: the moon wasn't always the quiet world we see today. Between 4 and 3 billion years ago, it likely had a churning, molten core generating a dynamo effect, where circulating liquid metal created a planetary-scale magnetic field. Earth's field comes from such a mechanism, but the moon's small size should have made this impossible. Its core should have cooled, and within a few 100 million years. So what kept the lunar engine running so long? One radical theory points to cosmic collisions. In its youth, the moon endured a bombardment of massive asteroids, impacts so violent they could have stirred the lunar core like a spoon in coffee, reigniting its dynamo with each strike. Another idea suggests the moon's orbit once brought it much closer to Earth, where our planet's gravity stretched and squeezed its interior, creating friction that heated the core. There's even a chance the moon's mantle may have acted like a giant blanket, trapping heat and delaying the core's cooling far longer than physics predicts. Whatever the cause, this magnetic era coincides with a time when the moon had volcanic plains and even a wispy atmosphere, a far cry from the airless wasteland we see today. Then, around 1 billion years ago, the music stopped. The dynamo sputtered out as the core finally cooled, leaving the moon exposed to the solar wind's harsh radiation. Without that magnetic shield, any lingering atmosphere was stripped away, and the surface became the barren landscape we recognize. But here's the twist. Earth's magnetic field is weakening today, losing nearly 10% of its strength every century. Could our planet face the same fate? The moon's story serves as both a cautionary tale and a stone, a reminder that even seemingly stable worlds are in flux, and that our cosmic backyard still holds mysteries as deep as those in distant galaxies. What's most humbling is realizing how much we've underestimated our closest neighbor. The moon isn't just a dead rock, it's a fossilized record of planetary evolution, holding clues about how small worlds evolve and what makes a planet habitable. Future missions to its unexplored poles and far side might uncover more surprises, proving that sometimes the greatest mysteries aren't light years away. They're right overhead, waiting in the silence of a cratered face we thought we knew. Our sun wasn't born alone. 4.5 billion years ago, it emerged from a swirling stellar nursery alongside thousands of siblings, a litter of stars forged from the same cosmic cloud. Today, those brothers and sisters are scattered across the Milky Way, lost to time and distance. But what if we could find them? This isn't just a celestial treasure hunt. It's a journey back to our solar system's infancy, a chance to uncover the conditions that made Earth possible. The search for the sun's lost siblings is one of astronomy's most captivating detective stories, and the clues are written in starlight. Every star cluster is a ticking clock. Gravity binds newborn stars together, but over millions of years, galactic tides and close encounters fling them apart like dandelion seeds in the wind. Simulations suggest our sun's original family may have contained anywhere from 1,000 to 10,000 stars, all drifting away at different speeds and angles. Some could now be halfway across the galaxy, their light dimmed by dust and distance. But they share one crucial trait with our sun, a nearly identical chemical fingerprint. Stars born together form from the same molecular soup, inheriting matching ratios of elements like iron, oxygen, and rare metals. It's like finding strangers who share your exact DNA. They must be family. Modern telescopes are turning this theory into a cosmic reunion. Projects like the Gaia Space Observatory have mapped the positions, movements, and compositions of nearly 2 billion stars, creating a galactic family album. By cross-referencing chemical signatures and orbital trajectories, astronomers have already identified a few candidates, stars like HD 162826, which shares the sun's unique blend of elements and moves as if it once danced in the same stellar cradle. The odds of a random match, less than 1 in 10,000. Yet the real prize isn't just bragging rights for finding long-lost relatives. These siblings could hold the key to Earth's origins. If we locate enough of them, we might reconstruct the solar system's birthplace. Was it a dense, bustling cluster where neighboring stars influenced our early planet formation, or a quieter corner where the sun grew up in isolation? Some theories suggest close encounters with stellar siblings could have nudged comets inward, delivering water to young Earth. Others propose that a nearby supernova, triggered by a massive sibling's death, seeded our solar system with radioactive elements that heated its building blocks. The search also raises tantalizing questions about life's cosmic odds. If siblings formed under identical conditions, did any develop planets like Earth? Missions like the James Space Telescope could someday study these distant cousins, searching for atmospheres with oxygen or methane, hints that the sun's family might harbor more than one living world. But time is the ultimate adversary. The older these stars get, the farther they wander, and the more their original motion is by galactic collisions and spiral arm passages. Some may have even been swallowed by the Milky Way's central black hole or flung into intergalactic space. Yet every new candidate brings us closer to piecing together our solar system's origin story, a tale written not in rock, but in the scattered glow of stars we've yet to name. The sun's siblings are out there, drifting in the dark. And with every technological leap, we get one step closer to bringing them home. In the vast emptiness between the planets, where sunlight fades to a dim glow and gravity's grip loosens, two spacecraft named Pioneer 10 and 11 quietly expectations. Launched in the early 1970s, these trailblazing probes were the first human-made objects to venture beyond the asteroid belt, their missions to study Jupiter and Saturn before hurling themselves toward the stars. Yet as they drifted farther from the sun, something peculiar happened, a mystery so subtle it took decades to notice, and so stubborn it still isn't fully solved. The pioneers were slowing down. Not from friction, space is too empty for that, but as if an unseen hand were gently tugging them backward. This tiny deviation, just a fraction of a nanometer per second squared, became known as the Pioneer Anomaly, and it's a humbling reminder that even in our own cosmic backyard, physics might still have secrets to share. At first, scientists assumed the explanation would be mundane. Spacecraft are complex machines, and even the slightest unaccounted force, a gas leak, a misaligned antenna, a flicker of heat radiating unevenly, could nudge their trajectory. The Pioneers, powered by radioactive plutonium, emitted heat as their generators decayed. Could that warmth, bouncing off their asymmetrical bodies, have acted like a microscopic thruster in reverse? Computer models suggested it might account for part of the slowdown, but not all. The anomaly persisted like a ghost in the data, whispering that something fundamental might be missing from our equations. Then came the wilder theories. Could the Pioneers have brushed against the fabric of dark matter, that invisible scaffold thought to weave through the cosmos? Or was theory of gravity, so reliable in our solar system, subtly breaking down over vast distances? Some physicists proposed modifications to general relativity, introducing tiny adjustments to gravity's behavior at the scale of the outer solar system. Others wondered if the anomaly was a sign of something even stranger, an unseen ninth planet lurking in the darkness, its gravity tugging on the probes as they passed. But the most tantalizing possibility, that the Pioneers stumbled upon a new piece of physics altogether. In science, it's often the smallest discrepancies, the barely perceptible wobbles in Mercury's orbit, the faint shifts in starlight that lead to revolutions. The Pioneer Anomaly had all the hallmarks of such a moment, a deviation too consistent to ignore, yet too slight to easily explain. It was as if the universe had left a breadcrumb, daring us to follow. Then in 2012, a team of researchers meticulously reconstructed every conceivable variable. The spacecraft's heat output, the pressure of sunlight, even the gravitational pull of distant objects, and found that thermal radiation alone could explain most of the anomaly. The case seemed closed, yet for some scientists, the puzzle never fully faded. The Pioneer's drift might have been a quirk of engineering, but the questions it raised linger like a shadow. What if, in our rush to solve the mystery, we overlooked something deeper? Spacecraft like New Horizons, now racing through the belt, could hold the answer. If they too show unexpected slowing as they leave the sun's domain, the anomaly might return with a vengeance. The lesson of the Pioneer Anomaly isn't just about a few wayward probes, it's about the humility of exploration. Even in an age of precision physics, where we can measure the spin of a black hole or weigh distant galaxies, the cosmos still has the power to surprise us. Sometimes, the smallest glitch in the data is the first thread of a much larger tapestry, waiting to be unraveled. And as the Pioneers coast silently into interstellar space, their faint signals long gone, they leave behind a legacy far greater than their missions intended. A reminder that discovery doesn't always shout. Sometimes it whispers, look up at the western sky just after sunset, or the eastern horizon before dawn, and you might catch a ghostly pyramid of light stretching upward from where the sun disappeared. This is twilight playing tricks on your eyes. It's the Zodiacal Light, one of the solar system's most ethereal phenomena. Sunlight reflecting off countless specks of dust floating between the planets, tracing the same path across the sky as the moon and planets. But this shimmering cone isn't just a pretty sight. It's a cosmic breadcrumb trail, leading us back to the violent collisions and icy wanderers that litter our solar system with debris. The dust itself is ancient, yet constantly renewed. Some comes from asteroid smash-ups in the belt between Mars and Jupiter, where rocky bodies pulverize each other into fine powder. Other particles are gifts from comets, icy nomads that shed material as they swing close to the sun, leaving behind glittering trails like celestial breadcrumbs. Gravity herds these motes into a vast, lens-shaped cloud centered on the sun, stretching from Mercury's orbit out beyond Mars. When sunlight hits this diffuse band just right, it scatters toward Earth, painting the sky with that otherworldly glow. What makes the Zodiacal Light so fascinating isn't just its beauty, it's how it connects us to the solar system's hidden architecture. That dust isn't static, it spirals inward over time, drawn by the sun's gravity in a process called the effect. As particles drift closer, they absorb sunlight and re-radiate the energy, slowing their orbit like a cyclist pedaling against the wind. Eventually, they plunge into the sun, completing a cosmic recycling process that's been running for billions of years. Yet the Zodiacal Light holds darker secrets too. In the 1990s, NASA's Clementine mission discovered a faint counterpart called the Gegenschein, a dim, circular glow exactly opposite the sun in the night sky, where backscattered light creates a ghostly mirror. And military satellites have spotted even more elusive structures, dust rings co-orbiting with Venus and Earth, likely trapped by our planet's gravity. These features hint at a dynamic system where worlds act like cosmic shepherds, corralling debris into invisible patterns. For astronomers, studying this dust is like reading the solar system's diary. The composition of those particles, whether rich in silicates from asteroids or organics from comets, reveals the balance between these two sources. Some researchers even suspect interstellar dust, swept up as the sun moves through the galaxy, might mix into the zodiacal cloud. Missions like Japan's have sampled such dust directly, catching microscopic grains in space and returning them to Earth like celestial archaeologists. But the most profound lesson of the Zodiacal Light is how it collapses distance. Those drifting motes are fragments of worlds we'll never visit, remnants of collisions we'll never witness, yet their glow bridges the gap between Earth and the depths of space. Every time you spot that eerie cone of light, you're not just seeing dust. You're seeing the solar system's breath, the exhalation of countless unseen bodies, and the silent evidence that even the emptiest corners of space are never truly empty. One of the most perplexing puzzles in modern cosmology isn't found in the distant reaches of space, it's hidden in the numbers. For years, scientists have calculated the universe's expansion rate using two fundamentally different methods, and the results refuse to agree. This isn't a minor rounding error. It's a full-blown crisis dubbed the tension, a discrepancy that threatens to unravel our understanding of cosmic history. On one side, we have meticulous measurements of the early universe's faint afterglow, the cosmic microwave background, suggesting an expansion rate of about 67 kilometers per second per. On the other, observations of pulsating stars and exploding supernovae in the nearby universe point to a noticeably faster rate, 73. That gap might seem small, but in the precise world of cosmology, it's a yawning chasm. Either we're missing something fundamental about how the universe works, or our tools are deceiving us in ways we don't yet understand. The stakes couldn't be higher. If the discrepancy is real, not just a fluke or measurement error, it implies the standard model of cosmology, our playbook for the universe's evolution, is incomplete. Perhaps dark energy, the mysterious force accelerating cosmic expansion, isn't constant but evolves over time, growing stronger or weaker in ways we haven't accounted for. Or maybe dark matter, the invisible glue holding galaxies together, interacts with ordinary matter in unexpected ways, subtly altering the universe's growth rate. Some theorists have even floated the idea of early dark energy, a temporary surge of repulsive force in the universe's infancy that could have left imprints on both the early and modern expansion rates without breaking other cosmological predictions. Then there's the radical possibility that our very framework for gravity is flawed. This theory of general relativity has passed every test thrown at it for over a century. But what if it falters on the grandest scales? Modified gravity theories with names like FR gravity or scenarios propose tweaks to the equations governing cosmic expansion. These aren't wild guesses. They're attempts to reconcile the tension without inventing new particles or forces. Yet every proposed solution comes with trade-offs, often creating new problems while solving the original discrepancy. The alternative, of course, is that the tension isn't real, just an illusion created by measurement biases. Could supernovae, our standard candles for gauging cosmic distances, be less reliable than we thought? Perhaps intervening dust or variations in stellar chemistry are skewing their brightness in ways we haven't fully corrected. Even the cosmic microwave background data, collected with exquisite precision by missions like, relies on assumptions about the universe's geometry and composition. If any of those assumptions are off, even slightly, the entire edifice wobbles. What makes the tension so electrifying is that it's not just a technical debate, it's a live experiment playing out in real time. New telescopes like the James Space Telescope and the upcoming Nancy Grace Roman Space Telescope are poised to deliver sharper data, potentially tipping the scales toward one resolution or another. Every fresh observation is a chance to either deepen the mystery or crack it wide open. This isn't just academic squabbling. The expansion rate sets the cosmic clock, dictating the universe's age and future. If the higher rate is correct, the universe might be younger than we thought, not 13.8 billion years, but perhaps closer to 12.5. That would force us to rethink how quickly galaxies and stars formed after the Big Bang. Conversely, if the lower rate holds, we might need to explain why local measurements seem artificially inflated. The tension is more than a numbers game. It's a mirror reflecting the limits of our knowledge. Whether it leads to new physics or better measurements, one thing's certain: the universe still has surprises up its sleeve. And as scientists grapple with this rift, they're not just recalculating equations. They're rewriting the story of everything. Digging into the Milky Way's past isn't just about gazing at serene spiral arms, it's cosmic archaeology, sifting through the wreckage of ancient collisions. One of the most dramatic chapters in our galaxy's history was uncovered not by spotting new stars, but by noticing the odd ones out. Meet the Gaia sausage, the remnants of a dwarf galaxy that smashed into the Milky Way 8 to 10 billion years ago. A cataclysm so violent it left scars written in stardust and motion. The story begins with the European Space Agency's Gaia mission, a spacecraft meticulously mapping the positions and velocities of over 1 billion stars. As astronomers pored over the data, they spotted something bizarre, a group of stars moving like no others. Instead of orbiting the galactic center in orderly paths, these stars hurtled on radial, plunging trajectories, darting toward the center and back out like cosmic pendulums. Plot their motions on a graph and they clump into a shape resembling a sausage, hence the whimsical name. But this was no celestial snack. It was the ghost of a galaxy long dead, its stars scattered like shrapnel from a primordial explosion. This wasn't just a random encounter. The Gaia sausage, technically known as the Gaia-Enceladus merger, was a dwarf galaxy roughly the size of the small cloud, packed with billions of stars. When it collided with the young Milky Way, the gravitational chaos didn't just add stars, it reshaped our galaxy's very structure. Simulations suggest the impact thickened the Milky Way's disk, puffing it into the halo we see today, while also contributing to the galaxy's inner bulge. Some astronomers even speculate the merger might have triggered a burst of star formation, igniting the birth of new stellar generations from the wreckage. What makes these stars so distinctive isn't just their paths, it's their composition. The sausage stars are metal poor, meaning they contain fewer heavy elements than the Milky Way's native population. That's a telltale sign of their origins. Dwarf galaxies, often relics of the early universe, tend to host older stars forged before generations of supernovae enriched the cosmos with elements like iron and gold. Their chemistry is a time capsule, preserving the conditions of a younger, more chaotic universe. But the Gaia sausage isn't just a fossil, it's a key to understanding galactic evolution. Collisions like this were far more common in the universe's youth, and similar mergers likely shaped most large galaxies we see today. The Andromeda galaxy, for instance, shows signs of its own ancient smash-ups, and in 4 billion years, it'll be the Milky Way's turn again when the two titans collide. By studying the sausage, we're glimpsing a process that's both destructive and creative, a reminder that galaxies grow not just by gently accreting gas, but by devouring their neighbors. The discovery also raises tantalizing questions. Did the merger deliver the Milky Way's first globular clusters, those dense balls of ancient stars orbiting our galaxy's core? Could some of the dark matter halo enveloping us be remnants of the sausage's own invisible scaffolding? Every answer peels back another layer of our galaxy's violent, vibrant history. So the next time you look up at the Milky Way's serene band of light, remember, that glow isn't just stars. It's the aftermath of a cosmic feast, the digested remains of galaxies that came before. The Gaia sausage is more than a curiosity. It's proof that even the grandest structures in the universe are built on collisions, and that every scar tells a story. That 72-second burst of radio static from 1977 still haunts us, not just as a mystery, but as a challenge. The WOW signal wasn't merely a blip in the data. It was a flare shot into the cosmic night, daring us to figure out whether we'd overheard a celestial accident or an intentional hello. Decades later, with technology light years ahead of the rudimentary equipment that first detected it, we're still wrestling with the same question. Was it a 1 in a trillion natural phenomenon, or evidence that we're not alone? Modern tools have sharpened the hunt. Projects like Breakthrough Listen now scan millions of radio channels simultaneously, using AI to sift through cosmic noise for patterns too subtle for human ears. Unlike the single antenna that caught the WOW signal, today's arrays, like the telescope array in California, combine hundreds of dishes, turning the sky into a grid of listening posts. They're tuned not just to hydrogen's frequency, where WOW appeared, but to a symphony of potential waterhole frequencies where civilizations might broadcast. The irony, even with this firepower, the signal's brevity makes it maddeningly hard to verify. Without repetition, it's like trying to identify a song from a single note. But what if WOW wasn't meant to repeat? Some astronomers speculate it could have been a fleeting burst, a cosmic lighthouse sweeping its beam across Earth for just an instant. Others wonder if it was a malfunction in our own technology, though no earthly source has ever matched its profile. The most tantalizing theory, it was a transmission, a signal aimed elsewhere that briefly grazed our planet, like overhearing a neighbor's phone call through thin walls. The search has evolved beyond radio waves. Optical SETI now scans for laser pulses, which advanced civilizations might use for precision communication. Meanwhile, the observatory will soon photograph the entire visible sky every few nights, hunting for artificial megastructures or flashes that defy natural explanations. Even gravitational waves, the ripples in spacetime from colliding black holes, are being eyed as potential carriers of deliberate messages. A language written not in light or sound, but in the fabric of reality itself. Yet the WOW signal's greatest legacy isn't just the tech it inspired, it's the philosophical shift. It taught us that absence of evidence isn't evidence of absence. The universe is vast, and 72 seconds of static over 46 years is less than a whisper in a hurricane. If civilizations are out there, they might communicate in ways we're only beginning to imagine. Quantum-entangled particles, neutrino beams, or something beyond our physics. So why keep listening? Because the alternative is unthinkable, that in a cosmos teeming with hundreds of billions of galaxies, we're the only ones asking the question. The WOW signal, whether fluke or greeting, reminds us that curiosity is our compass. Every tuned antenna, every algorithm scrubbing data for anomalies is a bet against cosmic loneliness. And until we know for sure, the sky remains not just a ceiling, but a mirror, reflecting back our stubborn, starry-eyed hope. For centuries, astronomers strained against the limits of their instruments, like sailors squinting at the horizon from a rowboat, until the James Space Telescope unfolded its golden mirrors in the void. This isn't just another telescope, it's a time machine. With infrared eyes sharper than any before it, JWST peers through cosmic dust like it's glass, capturing light that's been stretched and reddened by 13 billion years of universal expansion. The galaxies it spies aren't just distant, they're ancient, their light a snapshot from when the universe was a toddler, barely a few 100 million years old. And what it's showing us is turning textbooks to ash. Take GNZ 11, a galaxy so far away we see it as it was just 400 million years after the Big Bang. Conventional wisdom said galaxies this early should be small, chaotic blobs, but JWST revealed structures, spiral arms, disks that defy expectations. These primordial giants shouldn't exist, yet there they are, glowing defiantly in the data. It's as if we've dug up a smartphone in a medieval castle, forcing us to rethink how quickly matter clumped together in the universe's youth. Could dark matter, the invisible scaffolding guiding galaxy formation, behave differently than we thought? Or did some unknown process turbocharge star birth in the early cosmos? Every pixel from JWST feels like a puzzle piece from a box we didn't know we were missing. Then there's the telescope's other superpower, dissecting starlight filtering through exoplanet atmospheres. When WASP-96b, a gas giant 1,000 light-years away, passed in front of its star, JWST didn't just detect water vapor. It mapped clouds, spotted haze, even caught the chemical fingerprint of a world where it might rain molten sand. This isn't astronomy anymore, it's interstellar meteorology. And in the K218 system, tantalizing hints of sulfide, a molecule on Earth produced only by life, have set off a debate. Is this a sign of alien oceans or just cosmic chemistry fooling us again? JWST can't answer that yet, but it's handed us the tools to ask. But perhaps its quietest revolution is in the hunt for dark matter. By weighing ancient galaxies with gravitational lensing, observing how their mass bends light from objects behind them, JWST is testing whether dark matter particles are cold, slow-moving, or warm, faster, a distinction that shapes how galaxies form. Early data suggests the dark matter halos around these infant galaxies are smoother than models predicted, hinting that our maps of the invisible universe might need an update. What makes JWST extraordinary isn't just its specs, it's the questions we didn't know to ask. Like a child turning over rocks in a creek, every time it points somewhere new, it reveals wonders. Galaxies arranged like beads on a string, stars being born in the shadow of black holes, maybe even the first evidence of other universes in the cosmic background. This telescope isn't just rewriting history, it's teaching us that the universe's story is stranger, richer, and far more beautiful than we ever dreamed. And we're just turning the first page. The next chapter of cosmic exploration isn't just about bigger telescopes or faster rockets, it's about rewriting the rules of discovery itself. Take the observatory, rising from Chile's arid peaks like a sentinel for the stars. When it opens its eyes in 2025, this behemoth won't just observe the sky. It'll watch it, capturing panoramic images every few nights with a 3.2 gigapixel camera, the largest ever built. Imagine a cosmic surveillance system scanning the entire visible universe for changes, exploding stars, wandering interstellar objects like even the faint gravitational flickers of dark matter. But here's the real game changer. It could spot Planet 9, that hypothetical ice giant lurking in the solar system's shadows, by tracing its gravitational pull on smaller belt objects. This isn't just astronomy, it's a treasure hunt on galactic scales. Meanwhile, NASA's Europa Clipper is prepping for a voyage to Jupiter's icy moon, where an ocean hides beneath a frozen crust. Scheduled to launch in 2024, this armored explorer will skim just 25 kilometers above Europa's surface, using ice-penetrating radar to map its subsurface seas and a mass spectrometer to sniff plumes erupting from cracks. Why the frenzy? Because wherever we find liquid water on Earth, even in volcanic vents or Antarctic lakes, life follows. Europa's ocean, warmed by tidal forces as Jupiter's gravity flexes its core, might host hydrothermal vents not unlike those that birthed Earth's earliest organisms. The Kuiper won't land, but its findings could pave the way for a future drill probe, one that might finally answer whether we're alone in the solar system. But the most radical breakthroughs aren't just about where we're going, they're about how. Scientists at NASA's labs are testing prototypes for an electromagnetic propulsion drive, a controversial engine that could, if physics bends just right, generate thrust without fuel by bouncing microwaves in a closed chamber. Then there's the wild frontier of quantum communication, where entangled particles could allow instant messaging across light years, bypassing the lag of radio signals. China's satellite has already demonstrated quantum key distribution from orbit, and NASA's upcoming deep space quantum link aims to extend this to Mars. Picture a future where rovers on Europa stream data through quantum channels, or where astronauts navigate by constellations of entangled atoms. And let's not forget the dream that fuels sci-fi and science alike, warp drive. Mexican physicists' theoretical model, a spacecraft surfing on compressed space-time, once seemed pure fantasy. But recent calculations suggest negative energy requirements might be lower than thought, and labs are now testing nanoscale warps in metamaterials. We're not bending space yet, but for the first time, we're asking how instead of if. The coming decade will blur the line between imagination and reality. From telescopes that map dark matter's skeleton to probes tasting alien oceans, from engines defying Newton to networks tied by quantum threads, we're not just exploring space anymore. We're redefining what exploration means. And somewhere in the noise of data and the hum of prototypes, the universe whispers back, "You've only just begun." As our 26 celestial voyages draw to a close, one truth shines brighter than any star. The more we uncover, the vaster the unknown becomes. Every black hole's shadow we photograph, every whisper of dark matter we detect, every exoplanet's atmosphere we analyze doesn't simplify the cosmos, it deepens the mystery. The universe isn't a puzzle to be solved, but a story to be read, one where each chapter reveals new layers of complexity and wonder. Think of how far we've come. We've traced starlight back to the dawn of time, felt the gravitational tremors of colliding black holes, and even glimpsed the scaffolding of reality itself. Yet these aren't endpoints, they're trailheads, marking paths to discoveries we can't yet imagine. What makes this journey extraordinary isn't just the science, it's what it reveals about us. For all our telescopes and supercomputers, humanity's greatest tool remains curiosity. That relentless urge to ask why and what if has taken us from cave fires to quantum physics, from mythic constellations to mapping the cosmic web. When ancient cultures saw gods in the stars, they weren't wrong. They were early astronomers, using the language of their time to describe forces we're still unraveling today. The questions haven't changed, only our methods have. And that's the real magic. Science doesn't erase wonder, it amplifies it. So as you step away from these voyages, don't just marvel at how much we've learned. Marvel at how much remains. Those flickering dots overhead aren't just points of light, they're invitations. Every time you look up, you're joining a conversation that spans, one where every generation adds new verses to the universe's epic poem. Maybe you'll be the one to spot the next anomaly in telescope data, or inspire a child who will grow up to crack the dark energy code. The cosmos doesn't discriminate. It reveals its secrets to anyone willing to listen. Before you go, tell us, which voyage sparked your imagination? Was it the diamond planet glittering in the void, or the cosmic web stitching the universe together? The phantom pull of the Great Attractor, or the eerie silence behind Fermi's Paradox? Drop your thoughts below, and if you've enjoyed this journey through space and time, hit subscribe. Because this isn't goodbye, it's see you later. The universe has infinite stories left to tell, and together we'll keep turning the pages. Until next time, keep looking up, not just with your eyes, but with your heart. The greatest discoveries aren't just out there, they're within us, waiting to unfold.